He's my colleague. So yeah, Ioannis did his master's degree in electrical engineering and information technology at ETH Zurich. But then after a couple of, I must say, one internship experience at Swissre, he joined high power electronic systems lab at ETH Zurich again and started work on the power electronic systems. Then for 2.5 years almost, he has been working at Eurotube as R&D linear motor engineer. And he is doing all electrical engineering and power-related engineering systems at Eurotube. So yeah, Ioannis, you can take the words and yeah, just.
Thank you, Damla. Now I should share my screen. Is it full screen now?
Yes.
I guess so. Yeah. Okay. So thank you for Damla. Thank you, Damla, for the introduction. I'm Ioannis Stavropoulos. I'm R&D electrical engineer at Eurotube. And welcome at my presentation about the Maglev state of the art and future outlook for this Hyperloop seminar episode. Maybe this presentation will be quite technical, but I don't know the background of the audience, so I will try to break down some stuff as simple as possible. So what is the agenda of today? First, we'll start with an overview of propulsion levitation technologies in Hyperloop and the current state of the art. We discuss current propulsion trends, propulsion and levitation trends in Hyperloop and the narrowing down of tendencies. Next, out of propulsion and levitation, we focus mostly on levitation and compare the electromagnetic suspension and electrodynamic suspension. And we discuss some simulation results. And finally, we draw a conclusion and discuss the outlook. So let's start with the current status in the Hyperloop system architecture. As seen in this nice figure from a Hyperloop feasibility study of ICOM, there is a huge number of possibilities when designing a Hyperloop system. So we have multiple types of motors, like linear induction motors, linear synchronous motors, and so on. We could mount the motor on the vehicle or the infrastructure. We could also mount the suspension on the top, on the side, or the bottom of the tube. And finally, we could also choose between electromagnetic or attractive suspension or electrodynamic or repulsive suspension. And that gives us a total of 12 possible topologies, which is already too much. And it's a big conundrum on what to choose when designing a Hyperloop system, which is a pretty big decision financially and also infrastructure-wise. And as a result, you can see already that its organization active in Hyperloop is following its own standards in its own way. So others prefer vehicle side propulsion, others prefer infrastructure side propulsion, and so on. And we see everyone is all over the place. Fortunately, you can see that in the red rectangles that two main trends are emerging. It's either vehicle side propulsion with a repulsive EDS levitation, which has the benefits of a lower infrastructure cost and high reliability, and the cons of probably lower energy efficiency and lower air gap, which has the drawback that we need higher mechanical tolerances. And the other trend is a track-mounted linear synchronous motor with a top-mounted attractive levitation, as seen on the right-hand side of the graph. which probably has a higher energy efficiency and a lower vehicle mass and cost, but on the other hand has a high cost of infrastructure and can be less reliable and it's higher chances of faults. So what is the purpose of my work at YouTube and in general is to somehow decide on one standard out of all these possibilities and provide some hard numbers on which one is the best, deciding with some key performance indicators. Convert this into one standard architecture with limit costs and with enhance adoption of Hyperloop, of course. However, the problem, as stated in the comic on the right-hand side, is that when you create a new standard, the most possible outcome is not that you don't eliminate the previous standards, but you create a new standard on top. So, acknowledging this, let's move on and discuss about different levitation technologies. As I said, we will discuss on this presentation more the levitation aspect of architecture instead of the propulsion, because we feel that there is currently a larger gap in the literature. I feel that electrical motors are already well studied and documented. On the other hand, levitation is a way more niche subject, which asks for way more research. So starting with the first out of these two technologies, EDS, or electrodynamic suspension. This is a repulsive kind of suspension where the principle is that an electromagnet or a permanent magnet moving over an electrically conductive sheet like aluminum or copper will induce eddy electrical currents in the aluminum sheet, which will generate both a repulsive force and a drag force to the magnet. The pros of this technology is that it provides stable or passive levitation with no need to control the air gap. It can create a large air gap of up to 100 millimeters, which is it's nice for smaller mechanical tolerances and better safety. And also, it can be implemented with a really cheap aluminum track. Its cons are generally the high electromagnetic drag, which opposes the movement of the vehicle. The levitation is only possible at higher speeds, so it doesn't work at zero speeds. And also, there are undamped oscillations inherent in the system, which need to be damped. The equations that describe this form of suspension are shown in the top. On the left, it's described for the electromagnetic coils, on the right for permanent magnets. What is more important that you should keep into mind is the equation on the bottom, which is the lift-to-drag ratio. That is the ratio of the beneficial lift force to the drag force, which is useless to us. So we need this ratio as high as possible. And we see that this ratio depends on the track material properties, which is the magnetic permeability and the electrical conductivity, the velocity, and the physical length of the coil. In general, unless superconducting coils are employed, electromagnet EDS is generally quite weak. So for the rest of this presentation, we'll mostly consider permanent magnet Halbach arrays. What is a Halbach array, you may ask? In the top right, you can see what it is. It's an array of permanent magnet arrays that is assembled in a cyclical fashion, so left with a field facing left, bottom, right, up, and so on in a repeating fashion, so that in this way the magnetic field is concentrated on the one side of the array, creating a stronger field. And we have conducted a few series of finite element simulations, simulating neodymium permanent magnet Halbach arrays moving over an aluminum track. On the right, you could see the eddy currents induced in the aluminum track. And on the right, you can see the magnetic field created by the magnet as it moves over the aluminum sheet. Here we discuss the first results of our simulations. First, we inspect the effect of the air gap on the repulsive electrodynamic suspension. We simulated a few possible arrays with 5 permanent magnets or 9 permanent magnets, and at different sizes. As expected, we found out that the smaller the air gap, the greater the repulsive force. So this proves that we have a stable levitation with no control needed. The lift-to-drag ratio is roughly stable regardless of the air gap, and it's about 12 to 13 at 150 meters per second. And in order to provide some numbers that are more intuitive to the average person, if we consider 4 of these arrays, we get about 150 kilos of lift force with a drag force of about 112 newtons, which makes for a power consumption of 17 kilowatt at 150 meters per second. And this is not insignificant at all. This is quite high drag, and it's about equal to the aero drag of a car traveling at highway speeds at 120 kilometers per hour. So we say that EDS already, even at this really small scale, has quite high drag, which opposes the movement of the vehicle. Next, we see the effect of speed, and as expected, in the top lines, we see how the lift force increases as the speed builds up. And similarly, the electromagnetic drag drops in these bottom lines as the speed increases. We also found out that the lift-to-weight ratio, so how much of its weight a permanent magnet can lift, it's somewhat stable across different arrangements. It's about 60 to 70. So this array can lift about 60 times its weight at 55 millimeters and 150 meters per second. And finally, the most important metric, as discussed previously, is the lift-to-drag ratio. As expected, we see that it improves as a function of the square root of speed. And it also increases as a function of the size of the magnet, which is alpha in this equation. So this orange line is the array with the larger permanent magnets and features the highest lift-to-drag ratio, which is still not that good at 16. Other takeaways we have found from simulations is that stronger permanent magnets will, of course, offer stronger lift and a better lift-to-weight ratio, but do not improve the lift-drag ratio. We also found out that just a 12 millimeter thick aluminum track is enough to implement EDS because of the skin effect. The skin effect means that all eddy currents in the conductor really flow in the very top surface of the aluminum and not in its whole volume. So this is actually beneficial for us because we can save a lot on material. And also we did some simulations with a copper track, which can reduce drag by about 33%, but economically it doesn't make sense because for the same amount of volume, it will be about 4 times more expensive. Next on, we move on to discuss the other form of levitation, EMS, or electromagnetic suspension, which is an attractive form of suspension. This system uses magnetically attractive forces between a ferromagnetic track and an onboard electromagnet instead of the vehicle to achieve levitation. Its pros are its potentially very low drag. It also achieves levitation even at 0 speeds. And its lower magnetic field density means that less shielding to passenger compartments is needed. On the other hand, it provides unstable attracting force, so an active air control system is needed. It also needs an onboard power supply to power the coils. Also, generally, it can only act at narrow air gaps at about 10 millimeters, so we have really tight mechanical tolerances. And it requires expensive laminated steel tracks, which all the things we'll discuss in the following slides. Here we can see the formulas describing EMS. The top left formula shows how the attraction force is inversely proportional to the square of the air gap. That means the smaller the air gap, the larger the attractive force, which means that our attractive force is unstable and needs to be actively controlled. At the same time, we shouldn't forget that the same repulsive and drag forces that we discussed at EDS are still acting here at EMS. That means these forces counteract the attractive force of EMS and they reduce the lifted drag ratio a lot at high speeds. And this is something that people lots of times overlook when discuss about EMS and describing it as a dragless system. Similar to the previous case, we simulated a small electromagnet of about 200 millimeters times 60 times 45 with two coils of 3.6 kiloamps, which produces about the same type of lift with the previous Halbach array. So we have some roughly comparable results for a small scale vehicle. And on the left side, you can see the eddy currents induced on the track. On the right side, you can see the magnetic field. So what can we do to limit the drag forces? One simple trick that it's extremely common in electrical motors is laminating the steel tracks. This reduces the eddy currents a lot, and therefore the equivalent electrical conductivity of the track, according to this formula. And according to our simulations, simulating different track materials, starting from a solid steel electrical track and creating even thinner laminations down to 0.35 millimeters. We find out that the effective conductivity is reducing a lot. The lift force increases a lot. And the drag force can drop to essentially down to almost zero. This is at speeds of about 150 meters per second. To make this even more presentable to you, you could consider the blue lines in these three graphs, which represent the lift force. On the left-hand side graph, we have a simple solid steel track. We see how, when increasing the speed, the lift force quickly drops from 1600 down to 500 newtons, which means we lose almost 2/3 of our lift force simply because of the repulsive force of the eddy currents. Laminating the track down to 5 millimeters reduces the repulsive force by a lot, but there is still some small effect with the lift force dropping slightly. In the end, at the right hand, having really thin laminations of 0.3 millimeters effectively reduces the repulsive force down to zero, and we have the lift force being constant no matter the speed. Another benefit of EMS is its self-centering capabilities. That means we could possibly don't need any guidance system for the vehicle. That means controlling the side-to-side movement of the vehicle in the corners and so on. We found out by using a U-shaped track as shown in geometry 1 on the left-hand side, we create a strong self-centering force. That means when simulating a sideways movement of the vehicle for up to 20 millimeters, we create a really strong self-centering force which moves the vehicle back to the center of the track, which is another benefit of EMS compared to EDS, which is generally unstable on the side-to-side axis unless we create specific geometries for that one. This is all for the technical discussion, so maybe you can relax a bit right now. And moving on to the cost assessment of the systems, which is maybe the spiciest part of the presentation. As an engineer, our natural tendency is to favor the more efficient system, and then you would think, yeah, AMS sounds really great. But then there comes a time to foot the bill. And we have to discuss what is the operating and infrastructure cost of each option. Here in this simple table with some napkin math, we consider three possible options. First is EMS with thin laminated tracks. So as we saw, the most efficient option. Next, this EMS with non-laminated tracks, which is less efficient. And finally, the simple repulsive EDS system with also a simple aluminum track. I calculated the cost per kilometer of each track for this small scale system. So remember, this is simply a levitation system for a 150 kilo vehicle or so. And the cost per kilometer for a laminated steel track is about 1.1 million, which is already prohibitively expensive. Going with a lossier non-laminated track would be require about $500,000 per kilometer, while the EDS system simply requires $32,000 per kilometer. This whole difference is down to the fact that EDS can work with a really thin aluminum sheet, while EMS, the larger the vehicle, the more electrical steel you need also in the track side to make it work efficiently. On the other hand, of course, we have to consider that EMS is more efficient, so it uses less electricity to overcome its drag, and I calculated with some simple math the USD per kilometer traveled needed in electricity to overcome the drag. And it's quite low. I mean, in EMS is a few thousandths of the cent for a really small vehicle, remember. So how do we compare this to make this an apples-to-apples comparison? In the rightmost column, I calculated the passages needed for a vehicle to get your return on investment compared to EDS. And for this really small vehicle, you would need to travel about 100 million times to offset the cost of the efficient EMS system. Even, of course, this is a really small vehicle. Assuming that a full-scale vehicle would be about 100 times heavier or so, this would reduce by a factor of 100. So we could say that we need 1 million passengers to offset the cost of the EMS. So it still doesn't look really good for EMS right now. So what are the conclusions so far? The EDS drag forces are quite high and comparable to aero drag, so it's not really an efficient option. However, the infrastructure costs of the more efficient EMS suspension are highly unlikely to be offset by efficiency savings. My own opinion is that the high upfront costs linked with infrastructure are way more difficult to stomach for governments and investors compared to the running costs, which would hinder the adoption of Hyperloop. And this is what we at EuroTube deal mostly with, because we are really more infrastructure focused foundation. Magnetic levitation as a whole is either less efficient or more complex than even conventional steel and wheel rail. And this I will discuss in a minute. And also, future choice of suspension has to be carefully chosen to ensure efficiency, minimal cost, but also feasibility at ultra high speeds. So why do I mention steel on wheel rails that late in the presentation? As you can see in the graph below, I found in a paper linked in the source below. This discusses the drag coefficient, that is the inverse of the lift drag ratio of several modes of transport. At the bottom left, it's a conventional high-speed train, which is steel wheels on rails. And it's actually by far the most efficient at these low speeds, but there is a problem that we haven't actually tested it at the ultra high speeds, so we don't really know what is going up at the proposed speeds of Hyperloop. Then in this wide red band, you could see Hyperloop with EDS, which has a quite lower lift to drag ratio compared to steel rails. And at the white blue band, you can see aircraft, which is, of course, really inefficient. So narrowing down the possibilities, and what is our own conclusion so far at Eurotube? We think that the currently preferred architecture is a vehicle-mounted or short primary linear induction motor with a bottom-mounted EDS levitation and guidance, and a double-sided motor. The advantages of this architecture will be the lowest possible cost for propulsion and levitation with a single aluminum track. It would offer the best reliability both for the propulsion and levitation. The double-sided motor is not affected by levitation height. The aluminum motor secondary is also not creating any normal force to the guidance system, so it's not creating any problems on that front. And the passive levitation guidance means no control of the ergop is needed. Its disadvantages, of course, it's the small ergop required for the linear induction motor, the higher vehicle mass, because probably this vehicle will have to carry not only the motor, but also converters and even batteries. And also the cooling of the onboard motor, which is harder than track side. The unknowns of this option is the efficiency, and also the current collector feasibility, which could help to eliminate batteries. So finally, on the outlook, the infrastructure costs seem to outweigh operating costs when considering the choice of levitation technology. It is quite possible that we'll draw similar conclusions when we evaluate different motor types and topologies. For example, we may find that a simple linear induction motor may be more beneficial than a more efficient linear synchronous motor, simply because it requires a simple aluminum track to operate. And also EDS in its simplest form is quite inefficient, and cost-effective alternatives have to be investigated. So future work would be, on our side, would be to also investigate superconducting coils and EDS instead of permanent magnets. Also investigate a novel intact track EDS concept, which has a more complex track with copper coils, which also would increase the costs. The feasibility of steel wheels at ultra high speeds, because usually we associate steel wheels with high friction, but as we saw, this is not the case at all. They are actually quite efficient, but we don't know if they're feasible at 900 kilometers per hour or so. And I'm not a mechanical engineer to decide on this. And finally, also the feasibility of current collectors at ultra high speed that could also eliminate batteries and make short primary motors mounted on vehicles even more feasible. So this is the end of my presentation. Thank you very much for watching, and we'll be glad to take your questions.
Great, thanks a lot. There's already some questions for you, so let's dive right into those. First of all, the first question is, it reads, you mentioned briefly that some teams have the propulsion on the track and some of them I have the propulsion on the pod. Can you maybe quickly tell us how Eurotube is propelling and why you have chosen pod or trackside propulsion?
For our demo tube project, we have already chosen, so it's a trackside propulsion, but it's it's really a matter of simplicity. It shouldn't really count towards our future decisions. Demo tube is only a small-scale demonstrator of 120 meters. Powering it directly from the grid is simpler for us, comparing to having to deal with power systems on the vehicle, which is difficult to deal with inside the vacuum tube. Everything is quite simple to deal with from an outside container when having a track-mounted motor. But we're still considering our options when designing a full-scale system, which would be a final choice for the transportation grid all over Europe.
So there's one question that maybe hints directly at that. What would be your suggestion right now for a full-scale network then? And did you consider the combination of an infrastructure-based motor for acceleration with a vehicle-based motor for cruising?
Yeah. I mean, the first part of the question I already discussed. I don't know if the question was typed before this. I don't know if my answer is satisfactory. So this is what we're currently proposing. I am currently proposing personally. On the second part, yes, I'm familiar with this idea of having first a trackside launcher and then a motor for cruising. I'm not saying it's not an option. I think it's mostly a problem of combining both and making sure that, for example, the inactive motor is not interfering with an active motor and so on. So, because you have a motor and on board for cruising, but what does it happen when you also launch? So you have to have a different play. You have to consider the placement of each motor in the vehicle, which makes difficult topology on the vehicle. I think it's a compromise that maybe it's not that good. I would prefer a solution that it's either 100% one side or 100% other side, personally.
Okay, interesting. Then there's another question that says, what can be done to reduce the mentioned drag of the Halbach array? Are there any other things that you haven't mentioned yet?
Could you repeat? I didn't listen very well.
Are there any other any other measures to reduce the mentioned drag on the Halbach array?
Okay. Yeah. If I go back to the, can I go back to unfortunately, not very much. We have seen that the lift-to-drag ratio is mostly depending on the track properties. The only thing we can do is increase the size of the magnet and the direction of travel, which is the alpha parameter here. So increasing the alpha, the length of the vehicle, improves the lift-to-drag ratio as a function of square root of the size of the magnet. But of course, there is a limit how big a magnet you can implement. So yeah, that's it.
I like that you're directly going back to the physics and the formulas. Maybe one more question that also is in the same direction. Do you know if there's any ways to reduce the drag for magnets behind each other? So this relates to EMS drag. If there is no change in the induced magnetic field, so if you use the same pole of the magnets, will this eliminate most of the EMS drag? Because this is not possible in EDS. You have to have the changing fields in EDS. So in EMS, can that reduce the drag? And then how much will it reduce the drag if you have a scaled up capsule that has a lot of probably magnets with the same pole behind each other?
So I suppose they mean hybrid EMS, so a combination of PMs and a coil. That's why.
I think you could have that, but if you have EMS, I think that's what I've heard as well. It's like if you have the same pole behind one another in the direction of travel, if you have the same pole each time, if you don't change the magnetic field, because you don't need to do that in EMS, you need to do the changing the half array in the EDS, but in the EMS you have to have, you can have like in the direction of travel have like north, 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 and the same pole all over. In that case, does that reduce the drag because it has no changing induced? It's just the induction of the field in the guideway above is the drag. So if there is no induced field that needs to be induced and changes in the guideway, isn't that reducing the drag? And then how much?
I haven't investigated this option, to be honest. And intuitively, I cannot really give an answer. So, yeah, unfortunately, yeah, I have no answer on this one. It sounds like quite an unusual idea, I think.
I think there's somebody else who has an answer.
But if maybe if the person that asked the question can speak up, I don't know, maybe, and discuss this.
I don't know, but I think Gabriele just had an idea.
I wanted to ask you something about the I didn't write the answer. I haven't found how to add an answer there. I like to add a question. Maybe if you go to the slide about the simulations you did for EMS, and I would have two questions with that. Well, first of all, so this is the worst design possible for an EMS system, in the sense that the magnet is really wide in y direction, so perpendicular to the way of travel, and very short in x direction. And so what, for instance, we have done is to have in principle a very long magnet in x direction. And this is what at least we call homopolar EMS, which is different from one transrapid has, which is heteropolar, so always changing north-south, north-south. I don't have the number off the top of my head, but I know that it improves it quite a lot.
No objections here. On the first point on the dimension on the perpendicular, it didn't really make a difference in my simulation because it's really small anyway. And I wanted the two poles not to interact with each other. On the second, I also agree, but I wanted to limit the weight of the magnet to have some comparable, to be somewhat comparable with the previous Halbach array. So I'm sort of comparing apples to apples, you know. But as I said, also as I discussed, increasing the length in the side of in the direction of motion indeed improves the LDR and so on. So
that's probably a problem here with like small scale simulations versus full scale. At the end, when you have a full scale, all the physics, like the physics, it's not the physics changing, but the engineering and the approach changes quite drastically for EMS here. And I think EDS it really scales with the dimensions, but EMS doesn't, right?
Yeah. Maybe one question about the simulation setup. Is the 2 times 3,600 amperes actually what you like? Is it the right value? Because what happens then is that you saturate completely your core. So if it's steel, if you look at the magnetic field, the most you reach is 1 Tesla, which is the saturation of your steel.
Well,
and if
it
you try
doesn't because of the air gap. So.
I mean, maybe understanding this wrong, but the block on top, is it steel, right?
Yes.
And the most the highest magnetic field in that area is roughly over 1 Tesla, which is the saturation magnetic field of steel. So the usual thing, if you go with this crazy current, I mean 3,600 amperes, I don't think that would be feasible.
Remember, it's ampere time turns. It's
sorry?
not that crazy. It's ampere time turn. Ampere time turns.
Okay. But still,
it's the total total ampere current time turns of the coil.
Okay, I mean, just be careful, because if you reach saturation and you keep adding current, you are not helping it. Like EMS is limited to the saturation of the steel. Maybe also one other consideration I wanted to do about the EDS. I mean, in general, is the one thing, because we're doing a quite an extensive concept study currently internally, and one of the things we've realized is if you only optimize for one system, you come to a conclusion, but it's possibly making something else very troubling afterwards. So my example will be with EDS. If you have a lift to drag ratio of 12-13, right? That means your lift always has to be the mass of the vehicle. And your drag is then, in that case, slightly below 0.1 G, right? 1 G up lift, 0.1 G back.
Yep.
If you now scale it up to an actual vehicle, like let's say you have a 15-ton vehicle, which is possibly also on the lower end. If I did the napkin calculation quickly enough, it's 2.4 megawatts of drag. That's not going to happen. I can promise you that's never going to work. So this is we need to be careful when you consider one system and then another system suddenly explodes. So in particular, the propulsion power is really dangerous because of heat. So yeah, I mean, I do understand that the interest of EDS due to the lower like aluminum plate thing in the tube, but if it makes the system impossible, it's difficult as a solution.
Exactly. That's why my end conclusion is maybe why go maglev at all? I mean, if we somehow find out that the steel wheels can still work, we shouldn't rule out the possibility. Never.
It really depends on your top speed. Like I think steel wheels, I think above 500. That's what Siemens Mobility told me once. Is above 500, they wouldn't try. But I mean, you could. I don't say it's impossible, but
yeah, as I said, I'm not a mechanical engineer, so
probably also depends on the use case, whether you have switches involved or you want to do high-speed switching with it, which is then also like more of a problem compared to a single use case A to B, warehouse to warehouse or something.
But maybe for EMS, you could validate it with the values from Transrapid, because Transrapid was more efficient than a rail when it came like above, I don't know, 150, 200.
Something like that.
There has to be a reason. I don't know exactly how, but it surely was. So
do you remember if the efficiency was with or without the linear generator? Because it probably was without the linear generator, because the linear generator had a lot of drag.
Really? Okay. I remember just the graph that at some point the ICE crossed and so that was partially one of the reasons they wanted to accelerate quickly to go into the regime where we're more efficient. I can look it up. There is a nice book about Transrapid, and that graph, like several nice books, but one had a good graph.
Yeah, interesting. Nice discussion. Maybe we could wrap it up around here. We've all learned a lot. I've learned homopolar EMS, the word. I knew the concept. I didn't know what it was. So thanks. Thank you that we've all been able to learn about EDS, EMS, and all the different levitation and propulsion methods we can use. And with that, I would say let's see each other the next time, and then see each other next week, Monday at 18 o'clock. Have a good bye.
see you.
See you.
Bye.